Okay, so so basically, in case of sharpening filters, important mathematical operation is differentiation or derivative. So we considered profile of a row from one image. From this image, we considered this profile, and this is profile for the row which is passing through this bright spot. And then we quantized and sampled this profile. So this is quantized and sampled version of the profile. And for this row of pixels, as shown here, we determined first derivative and second derivative. And from these first derivative and second derivatives values, we have concluded some important points like first order generally produces thicker edges. Similarly, first order is useful to produce step changes or to detect step changes. Then second order derivative is useful for detecting isolated points. It is also useful for detecting fine details in an image like thin lines because it gives greater response for fine details than first derivative. Similarly, for isolated points, second order derivative gives higher response than first order derivative. So basically, second order derivative is useful for detecting fine details in the given image. Okay, and first derivative is useful for detecting thick lines or thick edges in the given image. And one more important conclusion, that whenever you are having constant gray values, whenever there is no transition in gray value, both these derivatives gives they give you zero response. So now, whenever you have image area with constant gray shades, this first derivative and second derivative operation gives you zero response, or it gives you very low response for slow variations in gray value. Okay, so these sharpening filters are equivalent to high pass filters. Okay, so high pass filters, they basically uh, give response to higher frequencies, and they attenuate low frequencies. In case of images, whenever there are transitions, spatial transitions, these are treated as high frequency components in the image. And as observed here, for these transitions, your first derivative and second derivative operation gives you greater response. Okay, and for very fine details like thin line and isolated point, second order derivative is useful. Okay, now one more observation, if you look at the step change, first order derivative gives you say value 7, and second order derivative gives you positive as well as negative value. Okay, so second order derivative usually gives double edge effect whenever there are step changes. Okay, so this positive as well as negative response, it appears as double edge when you visualize this thing as image. Okay, so this is one more important observation from this particular exercise. Okay, so whenever we are going for sharpening filters, this differentiation operation is very important. Now let us have a look at how we can design a mask or a filter, spatial filter, which can give us this sharpening filter operation or differentiation operation. Okay, so again start with one dimensional signal. So as shown here, this is one dimensional signal, and say this is your x-axis. Now how we can determine differentiation of this signal f? F in this case, this function f, say this y-axis f is function of only one variable, that is say x. Okay, so we can denote it as fx. Okay, and we can determine derivative or differentiation of fx with respect to x in discrete format as shown here. It is simply difference operation. If we consider, say, this instance as x, and if this instance is x plus 1, we can get derivative of f, a derivative of f with respect to x, which is simply difference between f of x plus 1 minus f of x. Okay. So if this is your x, this point on y-axis is your f of x. If this point is x plus 1, this particular point is f of x plus 1. So this simple difference, f of x plus 1 minus fx, gives you derivative of f with respect to x. Okay. So this is your first order derivative, right? Now let us see how we can determine second order derivative in general terms. Okay. So all of us know that second order derivative is nothing but difference of first derivatives, right? So say consider we have three samples, f of x minus 1, f of x, and f of x plus 1. Now we can write down first derivative for these three samples as shown here. Okay, so fx minus f of x minus 1 is first derivative. Then with respect to fx, f of x plus 1 minus fx is another first derivative term. And with respect to f of x plus 1, we need one more sample, next sample, that is f of x plus 2. F of x plus 2 minus f of x plus 1 gives us derivative at this particular point. Okay. Now, from these first derivative outputs, we can determine second derivative. So we can obtain second derivative as difference between these two first derivatives. Okay. So we can subtract this first term from second term to determine second derivative. Okay. So we consider this term f of x plus 1 minus fx minus, we consider first term minus f of x minus f of x minus 1. So effectively it gives you this equation. So second derivative of fx is given by f of x plus 1 plus f of x minus 1 minus 2 times f of x. Okay, because here there is one term minus fx, and when we subtract this term, we get one more minus fx. So effectively, it becomes minus 2 times fx. Okay, so simply we can obtain second derivative by subtracting two first derivatives. Okay. So there is one question that what is the above row? So this very first row, these are say three consecutive pixel values. Again, here we are considering one dimensional signal. That is, it means we are considering one particular row from the given image. Okay. So we are considering this middle pixel value, derivative of this middle pixel fx. Okay. And fx1 is a pixel previous to fx, and fx plus 1 is a pixel next to fx. So Sharon, is your doubt clear? So these are three consecutive pixel values. Okay. So these two terms, so give they give us first derivative. So first derivative is of fx is fx plus 1 minus fx, and first derivative of fx minus 1 is fx minus f of x minus 1, simple difference operation. Okay. And second derivative is difference of difference, or it is derivative of derivative. So as this is difference of difference, we take this term minus this term. This gives us second derivative. So finally, for one dimensional signal, like say one row of pixels, we get this equation for second derivative. So your second derivative is f of x plus 1 plus f of x minus 1 minus 2 times fx. Okay, so in order to determine second derivative of this particular pixel, what we can do, we simply add previous pixel with next pixel and we subtract 2 times current pixel. Okay, so hope this process is clear to you for one dimensional signal. Is there any doubt? Please type your doubt in the chat box if you are having any doubt. Okay. So for one dimensional signal, we have this equation for second derivative f of x plus 1 plus f of x minus 1 minus 2 times f of x. Okay. Now the same thing is indicated here. Now instead of one dimensional signal, when we consider an image, it has two independent variables, that is x and y. Okay, so we can have variation with respect to x as well as we can have variation with respect to y, because for pixels we have two coordinate values, x coordinate and y coordinate. Okay, so for images, instead of derivative, we have to talk in terms of partial derivatives. Okay, so as shown here, if this is your pixel at location xy, okay, it is actually f of xy, pixel value at location xy, we can indicate by f of xy. Now this is your previous pixel from the same row. So x-axis is decremented by 1, x coordinate value is decremented by 1. So this is your x minus 1 y position. And here you will get next pixel from the same row. So it is x plus 1 y. So when we consider variation along this horizontal direction, y remains constant. Okay, row value is same, means y is constant and we are varying x as x minus 1, x and x plus 1. Okay, so we can say partial derivative of function f of xy with respect to x. Okay, now this represents partial derivative. Partial derivative of function fxy with respect to x can be given by this equation, f of x plus 1y plus f of x minus 1y minus 2 times f of xy. So this is same as this equation. Okay, only difference is now we have added one more parameter, that is y, because now we are considering image signal. Okay, so image has x coordinate as well as y coordinate. And when we are determining derivative with respect to x, y is constant. Okay, so here y is constant and we are varying x. Okay, so equation partial derivative of f with respect to x is given by this equation. Okay, is it clear to all? Okay, so now similarly we for an image signal, we can consider variation in vertical direction. Okay, now we can consider this variation along vertical direction. Now, when we consider this vertical direction, column number is fixed, it remains constant. Okay, so for all these 3 pixels, column number is same, it is x, and your row number varies. With respect to xy, this becomes row y minus 1, and this is your next pixel from next row, that is y plus 1. Okay, so when we consider vertical direction, your partial derivative of image with respect to y, now it is given by this equation. Now in this equation, x is constant because your column number is constant. Okay, and here like this, now we have to consider 2 pixels which are from the same column and which are neighbors of xy. Okay, so next pixel to y is y plus 1, which is bottom pixel. So here we get f of x comma y plus 1. Then for corresponding to this location, we get f of x comma y minus 1 minus 2 times f of xy. Okay. So this is your first term is partial derivative with respect to x, and second term is partial derivative of f with respect to y. Okay. And when we consider partial derivative with respect to y, x is constant. Okay. So complete derivative for this particular neighborhood we can give by addition of these two partial derivatives. So derivative of fxy for horizontal and vertical directions is given by addition of these two partial derivatives. So we add dabba f by dabba x with dabba f by dabba y. Okay. And when we add these two equations, we get this equation. This minus 2 times fxy is added with minus 2 times fxy. So this gives us minus 4 times f of xy. And these four terms, that is f of x plus 1 y, then f of x minus 1 y. Similarly, we consider f of x y plus 1 and f of x y minus 1. Okay, so this is equation of derivative for a 3 by 3 image when we are considering horizontal and vertical direction variation. Okay, so from this equation, now we can design a mask which we can apply on 3 by 3 region to give sharpening operation. Okay, so from this equation, we can write the mask coefficients as shown here, right? Because if you look at this equation, your pixel under consideration, that is fxy, its coefficient is minus 4, right? So here we get minus 4. And for these four locations, that is horizontal neighbors and vertical neighbors, there is one term corresponding to each of these locations. So here, corresponding to these locations, weight value is 1, right? So we can get this mask minus 4, 1 here, 1 here, then 1 here, 1 here. And we don't have any term corresponding to diagonal locations. So at diagonal locations, we have a 0. Okay. So this is nothing but second derivative mask which we can apply on the image to determine second derivative or to determine output of sharpening filter. Okay, so these are the mask coefficients. Okay, so is this process clear how we have designed this mask 3 by 3 mask for second derivative operation by considering transitions along horizontal direction and transitions in gray shades along vertical direction. Okay, so hope this is clear to you. Now this second derivative operation is known as Laplacian operation, and that's why this particular mask is named as Laplacian mask. Okay, so this is an example of sharpening filter which is based on second derivative operation, and hence it is known as Laplacian mask. Okay, now here in this case we have considered transitions in gray shade along horizontal direction and vertical direction. Now, in addition to horizontal and vertical direction, there might be gray level transitions along diagonal direction. This plus 45 diagonal direction as well as minus 45 diagonal direction. Now, can anybody tell me what might be the central coefficient if we consider transitions in all possible directions, horizontal, vertical, plus 45 as well as minus 45. if we consider all these transitions, what will be value of central coefficient? Can anybody guess? See, in this example, we have considered only horizontal direction and vertical direction. Now, if we want to consider diagonal directions, we need to take derivative in diagonal direction. Yes, Sakshi, your answer is correct. Very good. Okay, let me explain how we can now construct a mass if we want to consider diagonal directions. Okay. Now let us consider this particular direction. Now again, this is your one-dimensional signal. Okay. So this your image f of xy. Now we can differentiate it along z1 direction. We can consider partial derivative of fxy along this direction, say z1. Okay. We are giving a name to this direction, say z1. So we can determine partial derivative of fxy with respect to z1. And in this case, these three pixels come into picture. This is your pixel under consideration. So you will get a term minus 2 times fxy corresponding to this direction. Then we have to take into account this pixel, which is f of x minus 1, y minus 1. And we have to consider next pixel, which is f of x plus 1, comma, y plus 1. Okay. So when we consider transition along this diagonal direction, we get one more partial derivative term, that is dabba f by dabba z1. Okay. Now we have to consider remaining diagonal direction, that is say z2. Okay. So as shown here, this is your direction, diagonal direction z2, and we can determine uh, partial derivative of fxy now with respect to z2. Okay. This is your one more diagonal direction. So corresponding to this z2 direction, we get one more term minus 2 times f of xy. Then in for with respect to xy, this is previous pixel. So we get one term f of x minus 1, y plus 1. And this is next pixel f of x plus 1, y minus 1. Okay. So this is partial derivative of fxy with respect to z2. And now if we want to consider all possible directions, that is horizontal, vertical, z1 and z2, we need to add these four partial derivatives: dabba f by dabba x, dabba f by dabba y. Then in addition to that, we need to add these two derivative terms, dabba f by dabba z1 and dabba f by dabba z2. So when we add all these four partial derivatives, now tell me what is central coefficient value. Okay, so in order to get derivative of fxy by considering all four directions, we need to add all these terms. Okay, so your final derivative of image fxy is given by dabba f by dabba x plus dabba f by dabba y plus dabba f by dabba z1 plus dabba f by dabba z2. And when we add all these terms, we get central coefficient value as minus 2 plus minus 2 plus minus 2 plus minus 2. So we get here minus 8. Yes, Mehak, your answer is correct. Okay, very good. Okay, so here we get minus 8. Okay, so for f image f of xy, derivative is given by addition of these four partial derivatives. So first for partial derivative is with respect to x, then it is with respect to y, then third partial derivative is with respect to diagonal direction, and this last term is with respect to second diagonal direction. Okay, so when we add all these terms, we get this particular mask. So central coefficient is -8 and it is surrounded by all ones. This is also an example of Laplacian mask because these mask coefficients we have derived by second derivative operation. Okay. So in previous Laplacian mask, that is -4 surrounded by 1, 1, 1, 1, we have considered only horizontal and vertical transitions. And in this particular Laplacian mask, we have considered all possible directions, horizontal, vertical, plus 45 diagonal direction and -45 diagonal direction. Okay. So this is Laplacian mask, which is used for detecting edges in the image. Okay. So these are variants of Laplacian mask. Now, if you look at very first mask, this considers horizontal and vertical direction. Now, this central coefficient is negative and it is surrounded by +1. Now, as in case of derivatives, we are actually considering difference, right? So instead of this, we can also use this mask where central coefficient is positive and it is surrounded by -1, -1, -1, -1. Okay, so this is also Laplacian mask, which is used for edge detection. Similarly, we can have one more variation for this mask, that is this central number coefficient -8. We can make it positive, that is 8, and it is surrounded by -1. Okay, so these are variants of Laplacian mask. Now let us solve one numerical based on Laplacian filter. So this is 5 by 5 image. Now consider this neighborhood, 3 by 3 neighborhood. This in green color, you are observing a pixel, which is pixel under consideration, and apply this Laplacian mask on this 3 by 3 neighborhood and tell me what is resultant value. Now, applying a mask is clear to all of you. We studied it with smoothing filters. Applying a mask means considering taking two-dimensional convolution of this filter coefficients with image area under the mask. Okay, so simply multiply 10 with 0, 10 with -1, then 210 with 0, and continue the process, and then add all these products and tell me what is your final result. Please type your answer in the chat box. Very good, Mehak, your answer is correct. Okay, so if we apply this mask on this 3 by 3 neighborhood, we get these are the product terms. We add all these 9 product terms and we get the result. Yes, Sai, your answer is correct. Soumya, you have done some mistake. Okay, so this is actually central value is multiplied by 4, so it is 40. Then there is this term is -1 multiplied by 210. This 10 is also multiplied by -1. This is multiplied by -1, and this is multiplied by -1. Yes, Manas, your answer is correct. So you will get answer as -200. Okay. So hope this process is clear to you, applying the mask. Now just move to next pixel, that is 210, and determine new value of this pixel by applying this mask on this neighborhood, which is shown in yellow color. Now I am expecting answers from other students. This applying mask is very simple process. So just type your answer for this 3x3 neighborhood. Yes, I'm getting few correct answers. Very good, Sakshi, Mehak, Manas. Okay, so here when we perform two-dimensional convolution between the given mass coefficients and this image area, you will get these product terms. Okay, so your central pixel value 210, it is multiplied by 4, and all other terms are as shown here, and the result of this is 200. When we add all these product terms, we get 200. Yes, Sai, your answer is correct. So good that all of you have given me correct answers. Okay, now similarly, if you go for next pixel, give me answer. You should give it very quickly. For this last pixel, we consider this 3x3 neighborhood. Okay, very good. Sakshi, Mehak, Soumya, Sai, all of you have given me correct answer. So we multiply central pixel by 4 and then we subtract these 4 pixels. Now as all of these pixels are having same value, we get 0 result for this third position. Okay, so when we apply this filter, sharpening filter on the given image, we are getting for central row, we are getting results as minus 200, 200 and 0. So from this, we can conclude that uh, whenever there are transitions in gray values, we are getting greater amplitude. Okay. So for very first pixel, there is transition from 10 to 210, and hence we are getting large difference value, which is minus 200. Then for next pixel, again, there is transition with respect to central pixel. So we are getting very large value. But when we apply the filter on constant gray values, we are getting 0 response. Okay. So from these results, we can conclude that sharpening filter gives 0 response to constant gray value area, or similarly, it gives low response to slow variations in gray value. Okay. It means sharpening filter attenuates low frequencies in the given image, and it gives greater response to transitions or details or high frequency contents in the image. Okay, so sharpening filters are useful for detecting edges and fine details in the given image. Okay, and as it attenuates low frequencies and as it gives response to high frequencies, this is equivalent, sharpening filters are equivalent to high pass filtering operation. Okay. So this is one more example, that is now instead of previous mask, now we are considering this mask, that is 8 surrounded by -1, means we are considering horizontal direction, vertical direction, as well as diagonal directions. Okay. So apply this filter on this 3x3 image. Okay, so the operation is as shown here. We can multiply these pixel values with respective filter coefficients, and then we add all these product terms, and this gives you output 600. Now, as we are also considering diagonal level transitions, response value is increased because here, like this horizontal transition of gray value from 10 to 200, there is also transition in this diagonal direction as well as this diagonal direction. That's why we are getting greater value. And if we consider again this particular area, if we consider next pixel, here there are constant gray values, and corresponding to this, you will get result as 0, right? Because if you apply this mask, -1 surround 8 surrounded by -1 on this image, your 8 into 210, it will be cancelled with all these values which are 210, and you will get a 0 value. Okay. So basically, these sharpening filters are useful to detect edges. So if we have this as original image, and when we apply sharpening filter or Laplacian mask on this image, we will get a result as shown here. So wherever there are transition, those values are highlighted, or for those transitions, we will get high response value, and for constant area, like here inside the ellipse, yellow gray value is present, and outside the ellipse, this blue value is present. So we will get for those regions, we will get 0 output. So here we are assuming minimum gray value is represented by this blue color. Okay. So when we apply a Laplacian mask, it basically detect edges or fine details in the image, and we will get result as shown here. Now, in certain image processing applications, if we are if we want to sharpen the image by preserving the background, what we need to add these detected edges to the original image, right? So that we get a result as shown here. Background is preserved and edges are sharpened, right? So we need to add this Laplacian of the image to original image to get this as resultant image or sharpened image. Okay. So now this operation, that is adding original image to Laplacian output, is equivalent to this operation. So this is your Laplacian 4 surrounded by -1. Now we are adding it to original image. Now original image means your pixel under consideration, right? So we have coefficient as 1 for the pixel under consideration, and it is surrounded by 0. Okay, so this Laplacian mask we can add to original image to get this another mask which is useful for image sharpening. So this 4 plus 1 gives you 5. Okay, so this process of adding original pixel value to Laplacian mask, this gives us another mask where central coefficient value is 5 and it is surrounded by -1. So again, if we consider this image, and on this image, if we apply a mask where central coefficient value is 5 and it is surrounded by -1, -1, -1, -1. So if we apply this mask on the image, we will directly get this result. That is, it preserves the background and as well as it sharpens the edges. So in order to sharpen the image by preserving the background, we can directly apply this mask on the given image. Okay, so this is also Laplacian mask, but this Laplacian mask is used for image sharpening, and this Laplacian mask is used for image smoothing. Okay, now like this mask, we can also have another variation of Laplacian mask for image sharpening, that is your 8 surrounded by -1, -1, -1. Okay, so this is your another Laplacian mask where we consider horizontal, vertical, as well as diagonal directions. Now, if we are using this Laplacian mask to detect the edges, and if we want to preserve the background by applying this Laplacian mask, we can derive another mask by adding this mask with 1 surrounded by zeros, and this will give us a mask where this central value is changed to 9. 8 plus 1 gives us 9. Okay. So here we can get central coefficient value as 9. So this is Laplacian mask, another version of Laplacian mask, which is useful for image sharpening. Okay. For image sharpening. Okay. So we can use either this mask 5 surrounded by minus 4 minus 1s or 9 surrounded by all minus 1s. These two masks are useful for image sharpening. Whereas 4 surrounded by 4 minus 1s and 8 surrounded by 8 minus 1s, these two masks are useful for edge detections or fine detail detection. And these two masks, that is 5 surrounded by minus 1 and 9 surrounded by minus 1. These two masks are useful for image sharpening. Okay. Let me erase this. Okay. Okay, so one example is shown here. So this is image of north pole of moon. Okay, now when we apply Laplacian mask on this image, we get this image. Okay, so in this image, edges are detected, but in this image, background is lost because here we have applied Laplacian mask, which is 8 surrounded by minus 1. Okay, now we can add this edge detected image with original image to get this resultant image. Or look at the last image. Okay, so compare this last image with very first image. If you compare these two images, you can easily say that here all the borders of these small objects, okay, or these small surface regions, all these borders are sharpened as compared to original image. So this is image sharpening operation. Here this image is generated by adding this edge detected image with original image. Okay, and this two-step process we can avoid by directly applying this particular mask. 5 surrounded by minus 1 or 9 surrounded by minus 1. If we apply this mask on this image, we can directly get this resultant image where this contents image, original image details are sharpened. Okay, this moon border as well as various regions from moon, these borders are sharpened because of this image sharpening operation. Okay, so this sharpening can be achieved in one pass by directly applying this mask instead of this mask. Okay, so hope this difference between these two masks is clear to you. This first mask is used to detect the edges, whereas this second mask is used to sharpen the image. Okay, so as shown here, here background is preserved and these various region borders are sharpened. Okay, so this mask is useful for image sharpening, whereas this mask is useful for detecting fine details. Okay, so hope these concepts of edge detection and image sharpening are clear to you. Now we move to next small topic remaining from your unit 2, that is unsharp masking and high boost filtering. Okay, so in unsharp masking, basic idea is to subtract a blurred version of an image from the image itself. Okay, so we can obtain sharpened image by subtracting blurred version from original image. So here F is your original image. A blurred is obtained by applying smoothing filter like averaging filter or weighted average filter. You can get blurred version of image, and by subtracting this blurred version from original image we can get sharpened image. Okay, so simply we can subtract blurred version from original image to get sharpened version, and this concept is known as unsharp masking. Okay, so basically we are subtracting unsharp of the image. Blurred version is nothing but unsharp of the original image. We are subtracting that version from original image to get sharpened image. This is known as unsharp masking. Now let us have a look at high boost filtering. Okay, now when we subtract blurred version from original image, we get details or edges in the image. Okay, now if we want to preserve the background, we can vary this original image. We can scale the original image by some factor A so that pre preserved background is varied. Okay, so that can be achieved by using this equation. We can multiply original image by A, and then we subtract blurred version of original image from this scaled image to get sharpened image. Effectively it is giving us sharpened image because we are scaling the original image, and then we are subtracting blurred version from the image. So this scaling has effect of boosting background. Okay, so that's why it is known as high boost filtering. Okay, now scaling original image by A, it can be represented in mask format as shown here. We are scaling pixel under consideration by A. Okay, so this is 3 by 3 mask equivalent to A into F. Now we can obtain blurred version by averaging filter. So this is also an example of weighted average filter or averaging filter, because if you look at the coefficient values, all of them are 1. Okay, so it is as if we are taking average over this 4 neighborhood. Okay, instead of 3 by 3 neighborhood, now we are considering only horizontal neighbors and vertical neighbors. So this is also one of the variation of smoothing filter, where instead of 3 by 3 neighborhood, we are simply considering 4 neighborhood. And all these coefficient values are identical, means this gives averaging effect. Okay, so we can use this mask for blurring the image, and by applying this mask we can get blurred version of image, and by using this mask we can scale the original image. Okay, so we are scaling original pixel values by A. Okay, and then we are subtracting blurred version from the image to get high boost filtered image. Okay, so corresponding to this operation, we can directly obtain mask for high boost filtering as shown here. Okay, we can get this mask by A into F minus F blurred. So this is your A into F. This is blurring filter. So this minus this gives us a mask which is equivalent to high boost filtering. So central coefficient value is A minus 1, and 0 minus 1 gives you minus 1 here. 0 minus 1 gives you minus 1. Similarly, minus 1 here, minus 1 here. Okay, so now this is your high boost filter mask. Now According to value of A, you can get different versions of high boost filter. So if your A is equal to 5, you will get this mask because your central value is A minus 1, 5 minus 1. So this gives you this mask 4 minus 1 minus 1 minus 1. So if you look at this image, this is nothing but your basic Laplacian mask, which is used for age detection. Okay. So if your A is 5, you will get simply output as edges or fine details. It won't preserve any background. You will directly get edge image. Okay. So this is your Laplacian mask for edge detection. Now, if we consider A at 6 in this example, if we consider A at 6, we will get central coefficient value as 5. Okay. So when we consider central coefficient as 5 and minus 1, minus 1, minus 1, minus 1, this is nothing but sharpened image, which is obtained by Laplacian plus image. Okay. So this is your mask. And when A is equal to B in general, you can have B minus 1 surrounded by minus 1. So you can select value of A, which is between 5 and 6. Okay. For any value between 5 and 6, you can preserve some part of the background. Okay. So maximum possible value of A is 6, which gives you here coefficient value as 5, which means we are adding entire background, or we are adding entire original image to the age detected image or Laplacian image. Okay. So usually for high boost filtering, we can set value between 5 to 6. Okay. So that's all for today's lecture, but don't leave the meeting. I want to discuss few important